Well, good morning, my chemist. Yes, I sound terrible. It feels like forever since we've chatted. Please forgive me if I sniff. My nose is so runny, but I am alive. Hey, you know what? We'll take that. All right, let's talk about conjugated systems. Go to our notes here. Now, what we've been building up to is working with the reactions of these conjugated systems. So we looked at their resonance structures, we looked what aromaticity was, all of those details. Well, now we're actually going to apply that, and we're going to start with conjugated generic systems, and then we're going to move into benzene. So for our conjugated systems, we are looking at polyunsaturated, which means it has more than one double bond. And again, conjugated, that means every atom has a p orbital. Now, just to be complete, hey, what kind of polyunsaturated systems are there? Well, accumulene is a very interesting one. So we have a double bond there, but the interesting thing is then there is another bond directly attached to it. But if you will remember your p orbitals, okay, your p orbitals have to line up. Go back to blue. So these cumulenes are very unique because this one would line up with, okay, that is the most horrific drawing. But if you will, the blue ones are in the P, let me see, I have it in the Y direction, and the red ones are in the PZ direction. So they're actually not in the same plane. These are in the PZ. So if you were to draw this, go back to black, it would look like that, yes, but one of them would be out of the plane and one of them would be in the plane. Now, again, not very common. That's not the system that we're going to deal with, but it's definitely worth noting because there's some chirality too. So that's the last time I talked about it. All right. And then what about isolated systems? So you can have as many double bonds or triple bonds, basically p orbitals, as you want. I'm only interested in the ones that are conjugated. So isolated means that the p orbitals are not adjacent to each other. And conjugated, of course, means every atom in that system has access. That one would be conjugated. All right, well, what are my variations? Okay, you can have double bonds, you can have triple bonds. If you have two, that is called a diene. Ha ha ha. I know, that's the one that we make jokes with. Diene and triene. Okay, this one specifically is called 1,3-butadiene. So, of course, if you had three, one, two, three, that would be called triene. Organic chemistry is so trying. And I just try, but I'm dying trying to do it. Okay, so lame. I know, but I just had to throw that in there. All right, so you could just name them appropriately. Now, there is a special one called isoprene. And if you'll notice, it looks like the 1,3-butadiene and it just has an extra methyl group. So you can have any variations thereof. Can you do this with triple bonds as well? Sure. The only requirement to be conjugated is that they have p orbitals. What about combining the two? Yes. One, two, three. Okay, it's really the p orbitals that I'm not in, or that I'm interested in, not necessarily where they came from. All right, so that is a polyconjugated system. okay, or a polyunsaturated system that happens to be conjugated. And then I have a little question here, just, hey, can you identify which ones are isolated, which ones are conjugated? Okay, I still find it the easiest to draw the p orbitals, and if the p orbitals are all in a row, oh, they're all in a row, so this one would be conjugated. Okay, so I give you a few examples there. All right, the next thing I want to talk about is bond lengths. Now, this is a very important part of the conjugated system because the bond lengths aren't exactly as we expect. So just generically, a carbon-carbon single bond is about 1.54 angstroms, which is times 10 to the minus 10th. All right, a double is about 1.34, and a triple is about 1.20. Okay, so that's what we typically see. But there are some special characteristics when you start playing with conjugated systems, specifically when you get really conjugated into your aromatics, and that is they pull on the bonds that are next to them. So for instance, right here, I have my double bond, okay, my pi system, and it's pulling on this bond, and it's pulling just a little bit harder than just a regular single bond. So it doesn't change by much. Okay, so 1.50 versus a 1.54. Okay, not much. But let's look what happens when it's in a conjugated system. Okay, so I'm looking at this one, and it drops all the way down to 1.47. So you could almost say it has double bond characteristics, and that's what delocalized means. And that's why you draw resonance structures, because there's not one of them, it's a hybrid of all of them. So this is even smaller because of the alignment of all those p orbitals. And so it's just even a little bit smaller. So it's 1.47 versus 1.54. Okay, significantly smaller. Does it do the same thing for a triple bond? Why, yes, it does. All right, now a triple bond has two um, pi bonds, so should it pull it even tighter? And the answer is yes. Okay. I mean, not a ton, but keep in mind these are bond lengths, so even a little bit matters. All right, so 1.46 if it's connected to a triple bond. Well, what about in between a triple bond and a double bond? We would expect that to be even shorter. And this bond right there is 1.43. So we have progressively gotten shorter. So what would be the shortest one we expected? Between two triple bonds. And we can get all the way down to 1.37 angstroms. So those carbons are pretty close together. All right, take home message. Conjugated systems are exceptionally stable because they have the delocalized p orbitals or the pi system, and that will affect the overall bond lengths. Okay. Can I put my money where my mouth is? Why, yes. Let's actually look at some stability and then something called conformations. Now, we haven't done this in a while, conformational analysis. Remember, those are not resonance structures. Okay. I am just rotating around bonds. And so this little S right here, that stands for around the single bond. All right. So this one, again, is my diene, but it would be called, no, that's an S, S trans, because around this bond right here, around that bond, that is in a trans configuration, okay, because these are opposite of each other. Okay, that's different than a trans alkene, so that's why we put the little S in there. All right, so what's another conformation? Okay, if you rotate, kind of like a Newman, this one would be called S cis. All right, what are the pros and cons and the stability of them? Well, of course, there's only two answers in organic chemistry, sterics and electronics. This one, of course, is more stable because it has less sterics. Where that cis conformation, just like in alkenes. In fact, if I was kind of to draw those hydrogens, they're almost running right into each other, right on top of each other. So this one is less stable. Well, I'll put more sterics, less stable. But guess what? If it's less stable, it's more reactive. So your dienes are actually more reactive in the S-cis conformation than they are in the S-trans. All right, but do I have any numbers that can go with this? Let's take a look at some hydrogenation. We'll use palladium on carbon. All right, so this is an isolated diene, and it is going to hydrogenate just to 1, 2, 3, 4, 5 to pentane. Well, that delta H, okay, have to look this up. Is a negative 61 kcals. What? Kcals? We don't use kcals anymore. I know it's an organic thing. All right, so it is negative. Okay, it's exothermic, and so 61 kilocalories came off per mole. Thank you. Not very helpful yet. Well, let's do the same thing, only let's make it a conjugated system. So it's still just two pi bonds that have to be hydrogenated, but this time, double checking 54. Okay, why the difference and what does the difference mean? All right, so this one gave us less energy. If it gave us less energy, that must be because the molecule it came from was more stable. So the heats of hydrogenation actually confirm this special property of conjugated systems in that they are more stable. Remember, anything that's more stable is generally less reactive. But we also know that in the two conformations, the S-cis has more sterics, so it's less stable, so it's more reactive. All right, we're going to do some reactions here in a minute, but for this problem, just approximate the bond lengths for each of the following. All right, so, and again, I'll use the table above. You would go in and say, well, that's a double bond. I think that's about 1.34. And that's a double bond. I think that's 1.34. But the real question is, what's going on right there? Is it conjugated or is it not? Now it's going to shorten either way, but in this case, it's conjugated. And so I peek up here, and for the conjugated, it was 1.47. What about that one, though? That is not part of a conjugated system. That is just attached or an allylic location. And so that one we'd say is 1.50. Again, do they have to be those exact numbers? No, it's just putting things into perspective, comparing them to each other. All right, that is conjugated systems. Until next time, jolly out.